Super privileged to have Hala Nelson here. She has a book. Super cool. Professor at JMU in mathematics, wicked smart. Again, she spoke last year. Super privileged again to have her here. So let's all give her a big round of applause.
Thank you. I guess this is, can you hear me? Mic check. I guess I can hear myself. So, okay, so my name is Hala Nelson, and I am an associate professor of math at James Madison University. I recently veered into data and AI because I felt like that is where someone can help advance, so a mathematician can help address so many problems under one way of thinking, under like one underlying structure, because I've seen over and over again, I specialize in mathematical modeling, and I've seen over and over again how the same mathematics can help address so many types of problems, and you're going to see that in my talk and in the book, and etc. Okay, so one thing about this talk is I usually have my laptop with me and I scroll down. I don't like click slides, so when I realized I'm not going to have my laptop with me, I'm going to have the very nice persons in the back scroll down for me, and it's going to be interrupted many times, this talk, the way it's going to happen. But we're going to start scrolling down. And I'm happy that my talk came after the two keynotes because it relates to both of them. So the second keynote asked about what makes us human, and I ask about that all the time. And I actually also go one more question is what makes us intelligent? How do we define intelligence? Because we cannot talk about artificial intelligence before actually wondering what is it that we're trying to make the machines do and create if we haven't thought about our own intelligence and trying to replicate that in a machine. So I kind of sat down for a long time, tried to like put all the aspects of intelligence in one picture on top of a human head. And then I came up with these, and I usually have more time, but I don't have today. I usually ask people, look at this, and do you think we have more aspects? Did I capture all aspects of intelligence in this infographic? Or not, and if not, please tell me what you define as intelligence that I did not capture here. And remember, if we want to create intelligent machines, we have to replicate all these aspects of intelligence and have them communicate with each other. Okay, we have to create models that do that. So, of course, we have the first aspect of intelligence. I'm not going to go over all of them, but the first aspect would be perception. We perceive our environment. We understand what we perceive. And our perception happens through our sensory receptors, like the vision, the hearing, measurements, etc. We kind of, and every time I say something in this infographic, whatever I happen to go over today, think about the computer models that are doing that, the mathematical and machine models that are, doing computer vision, auditory, you get sensors all over the place, you get their measurements, and you do something with their data. So you can every time you go on the internet and read about something in AI, it can be mapped back to trying to model part of this picture here. And there's a big part of our intelligence is, for example, reasoning. We have we are human beings who are able to reason and not only capture patterns from the data, right? Like the language models that the first keynote was talking about, they're capturing patterns in the data, but humans do more than capture capture pattern is just one, just the beginning, but we can also logically reason about that. And how do we do mathematical models that do logical reasoning as well, like causal reasoning? We actually experiment, we do causation, and we have to create mathematical models that can reason in a cause, like this event caused that event. It's not merely correlated, okay? So this is kind of whenever I talk about things, you're always mapping it back to this picture. And of course, there's the big picture, the big question of awareness, which we cannot replicate mathematically or define even. So that's more like in red. But everything else over there, that's navigation, computation, imagination, like generation, right? That's all. We have models now that can talk to that, mathematical models and machine models that are actually succeeding in creating intelligence. Okay, so if you could scroll down a little. Yeah, more. See, there's more of that stuff. There's the empathy aspect, and the second keynote was talking about the human. What makes us human is we actually empathize with each other in a way that machines still can't, but maybe they will. So just scroll down a little. Of course, we also have reproduction. If you want like full intelligence, you have to be able to replicate yourself. All right, so if we could just scroll down a little. That's going to slow us down. So who knows how far I'll go today. Okay, so as I said, we want mathematical models. So the nice thing about all of this, when you look at AI, data science, you have this like information overload. You're like, where do I even start, and how do I even understand, like get a full picture of what the field is about, or how to even get into it. And my argument is like, if you know math, the math underlying, you should actually get into it very fast, because a lot of these models are doing one of two things, and I'm going to say what they are today. So the first thing is this is like the big picture of what usually happens on models for computer vision, for natural language, for a lot of these models, even like most of machine learning models, all of them, they're always doing like this row, you know. So you input any type of data, and then of course machines. The way we created them only understand numbers, so and actually not any numbers. Like you have to always go to the binary eventually, but let's stay on the level of numbers. You basically input, you vectorize, you change your data, whatever type of data you have, into numbers, vectors, matrices, tensors, whatever, either a bunch of numbers. But then, sadly, I mean, we have so much information, so much data. Like, for example, if you're doing language, you have corpuses, you have like millions, sometimes billions of dimensions. Of course, we don't have machines that can process that amount, that high dimensionality as it is, right? So you have to do something to reduce the dimensionality, and that's where the math people come, and they create all these ways to reduce dimensionality of data. So that you can process it on a machine, and then so that whatever model can process it, and then you end up passing this data that now is organized, and you can feed it into some math function. And then you output, a function. And, the first thing you do in math is everything is a function in math. So you just take an input to produce an output. So say you take, the last model, say, of GPT-4 takes any input and creates any output, like takes text, creates the outputs vision. But if you find a way, in my math head, is like you're just creating a map that this is from this space of, I don't know, text to this space of pictures. And then if you can like model that in terms of numbers, then you should be able to. It's not magic. when you actually think about it mathematically. And that's, I mean, you stop seeing like, oh my gosh, this is crazy. It's not that crazy if you think about it on the math level, exactly what's happening. And of course, you have to test and improve. And then the question is, well, what are these magic functions that people are using and succeeding? That's the thing, is in math, you want a function that has an expressive ability, right? And the nice thing is you don't have to write these amazingly complicated formulas. You know, in nature is very, how would I say, it tries to do things in a simple way. So these functions that have succeeded recently in expressing a lot of for example, computer vision, and this expressiveness is coming from simple type of functions, not from your most hard mathematics. It just starts with linear combinations, and then if you linearly combine features, meaning if you take weight for this first feature, and if you put a feature, give this much weight to this feature, that much weight to that feature, etc., and then you just add them up, and then you just do something. Okay, life is not linear. You have to introduce some nonlinearity there, but the nonlinearity is simple as well mathematically. But the success came from the hierarchy of doing things over and over again. And in math, again, it's not hard because in math, we approximate things. The nice thing is you just you have a complex thing that you want to express. You can approximate it by many you don't like express it as it is in one shot. You can approximate it by a sequence of simple things, and once you know what that sequence of simple things, you can add it up or compose it up to the complex thing. So basically, even if you dive into the math that's going on there, it's still not that hard. So there's two types of things that people do to if you're doing AI, you're like working with some models, whether for a language, for whatever. Your question is are you doing? There's two types of big schools that people do. It's either deterministic or probabilistic. Okay, it's really only that. So they're trying to learn like this pattern of data. They're trying to learn what makes this picture a dog, and what makes this picture. I think you showed the picture of layered in the fridge, what's in the fridge, right? And what to make out of that. So if you're trying, there are many models mathematically that you're trying to learn a function that expresses that. So there's many models. You're like, which one am I going to use, or which one is better, etc. The question you want to ask yourself before that, if you don't want to get lost, is what type of models are they using, and what's good and bad about each of these types of models. Before diving in the models, you have to know if it's so if you could scroll down a bit more down. Yeah, this is enough. Okay, so it's either like really deterministic models or probabilistic models. And in a deterministic model, you know exactly what function you're looking for. You actually write it down. You're like, yeah, give me the x's and I'll give you the y. Give me the features. The x's are like the features of the data or the image, the pixels or the vectors that represent the words in your text. Give me the input, and I have a function that is written down, and then it will take it and will produce an output. And you're actually trying to learn exactly what the parameters of that function are. Okay, and you learn it from trying not to make errors, so you want to minimize the error, etc. So there's optimization going on there. But then the probabilistic models, it's a different kind of school, different set of models. They also they are the ones that I actually like, even though my training isn't deterministic. I actually like probabilistic better. It is so basically, instead of saying exactly what the function that's producing this output is you wanted to learn the probability distribution of the joint probability distribution of the features. So basically, how likely is this output to occur with these features of the data? And that's what you're learning. And of course, the data is very high dimensional. So it's not one probability distribution. It's like a joint probability distribution. So, so the question then, the difference in models, other than deterministic probabilistic, is exactly how they're writing down these probability distributions. Like you decompose stuff, how are they, what kind of assumptions are they making on the probability distribution that they want to learn? And are they like, is it a simple one? Is it explicit? And then once they have the original assumption on what kind of object they want to learn, whether it's a deterministic function or a probability distribution, then exactly how are they going about learning it, meaning how are they doing the optimization, how they're doing the minimization, how they're doing the maximization, etc. So once you like realize that the differences are just in the assumption and how they're going about finding the parameters or how they're going about, then it just all becomes like similar in your head. And you're like, oh, okay, that's not really that much magic. Okay, so if you could scroll down a little. Scroll down. Okay, so if you could like zoom out. No, back. See, we're gonna like always stop and do this. So if you could just go down slowly, a bit more, more. Well, this is like our break. Okay, so a bit, yeah, and then yeah, I want to see these together, the green spots. Yeah, one more green spot. Okay. Here we go. So of course, in this field, there's like the theory, the models themselves, what they do, like I was just describing, but there's also the application, all kinds of application, and then the application and the theory can still be more on like you're sitting alone, you're not really getting your hands dirty. But the moment you want to implement your models, that's when you start getting your hands dirty, and that's when you start needing TensorFlow and Python, and if you want to scale, if you want to do say machine learning at a big scale, that's when like the actual difficulty that we in math and applications we don't think about much. We just, like for me, if you want to scale mathematically, you just take n to infinity. You don't really sit down and try to create a machine that takes all this data, and then the limitations start becoming real once you get on the implementation and engineering side. All right, so in the book, this book that I wrote, it's about more of how it's all, you see it from above, and all the math that you need in it, which I promise is easy. And the applications, all kinds of applications, and I connect them all the time together so people are not lost. But I don't do implementation and engineering, and that's in my opinion, is the harder part. I'll do it in the next book after I learn it. And then if you could scroll down a little. All right, a bit down. All right, so again, if you really want to learn the whole story, you have to think about everything like from end to end. For example, like the data, its sources, to data storage, data lakes, data warehouses, data architectures, like how to manage it, how to retrieve it, and also like you have to do communication and information science. You have to also think about the hardware and the chips and the solid materials, what to optimize for. And if you want to go next to I think like the future is the quantum computing side of things. Then you have to go literally down to the solid materials and to the quantum level and how to affect, like how an electric signal you can control like polarity of things and so anyway, so if you really want to like learn and keep learning and do AI, because then you have to like eventually do it all the way from like the hardware that supports the software, and think about it in our humanity as the biological system, that the biological underlying infrastructure that we have that supports our consciousness. So a bit down, and actually I will talk about all of that in the next book. So if we keep going, yeah. So let me see how much time I have. Stuff I want to go over. Okay. So I just want to say that in AI, a lot of people think AI is only machine learning and only neural networks, and but it's actually not. It's really everything. It's like the underlying. It's for example, this is an example that is from Nature Communications. It's about the self-organizations in nano. It's a nano-robotics applications, like these little nano-robots that you can design, and eventually the hope is like you send in the blood, you send in the bloodstream, and then they communicate with each other, they release medicine, etc. So there's a lot of math that goes in there. For an example like this, like self-assembling nano robots, there's a lot of math that goes in there that is other than just neural networks. So it depends what field you are, but again, the math. My point is the math simplifies all of this story together and helps tell a good story. So if you go down, and there's this example about these nano robots that can eventually go into the blood stream, etc. In my mind, when I'm reading that article, I'm like, well, show me the math. I want to see exactly. I mean, it seems like self-assembly is there's some particular math that will be, they're defining, that's driving the motion of these, what's the underlying math that drives the motion of these robots, nano-robots, and then to define the math, and then they self-assemble, and then they produce a big structure that communicates information. So there's an underlying microscopic processes that can be translated on a bigger scale and produce something. So when you see the math, it's not really that. If you have a trained eye, if not, it's okay. But if you have a trained eye, the math of this is not complicated at all. It's just a function, a vector defining the position of these robots and how the position evolved with time. And there is, of course, a dependency on their orientation. And then, of course, if you want these robots to communicate with each other mathematically, you have to put an interaction term. So this is not a slide for you to understand, but it's more of a slide that explains that usually what's going on, if you want to model things like that and drive them, you can model them mathematically easily. And for a trained eye, it's not that hard. It does look in the outside world as magic, but mathematically, it's usually predictable what's going on. So if you could just scroll down a bit more, or finish the slide, just scroll down. And keep scrolling. Yeah, okay. A bit more. Sorry about that. We're always going to have these interruptions. Usually I have my laptop and it flows way more smoothly, but I knew this wasn't going to be smooth when I realized I don't have my laptop. I can't have my laptop on me. Okay, so So, so let's see the type of applications and how math underlines all of those. So, right, so the projects I've worked on. So of course, my thesis is math unifies all of these data and AI models and in a simple way. So the type of projects I have worked on, so if you go down a bit more. All right, so these are the projects I usually gravitate to. So it's always about logistics transformation. I'm trying to get more into the food sustainability, the food pact. I don't know if you all have heard about that. And I like doing projects in like addressing poverty in the world and health and well-being. And I also always, so if you go a bit down, and I always also gravitate to the military applications because I grew up in Lebanon, so you can imagine why I love the military applications and the defense, actually, applications. I think it's very important to use math and AI for defense projects. So I've done projects in these, and if you keep going down. OK, so we worked with the fire department in Harrisonburg City. They have all kinds of data, incident data, and incident data like the fire incidents and the population, the type of call. So they have a ton of data. And then we had to join it with the population data, and then they wanted to know where to build, what's the best location for the next fire station. So there's a lot that goes in there. There's the optimization, like where to put, what's the best location based, and where's the most, to get most coverage, what's most likely. So there's a lot of geographic systems going in there, and so much. So that was one of the big data projects we worked on, and now they're building the fire station based on the students' analysis. And we also did work with the Harrisonburg City of Public Transportation. They wanted to have they wanted to assess their performance, the supply, demand, if the routes they were doing them by hand. And by the way, humans do machine learning in their head. And if you give someone, if you bring in an experienced person who's been working their city all their life, and you bring us to look at their data and do the routes for them optimally, like with mathematical calculation, it's not that different. They actually do it in their head, and they do it well. So sometimes it's like how much you really need us. But sometimes they need us just to tell them that what they're doing is good. But anyway, so we worked on all kinds of stuff. We worked with the military, the Air Force. The Air Force wanted to bring blockchain into their logistics operation. So we had to kind of convince the military that that is not a bad idea. And but everything is very slow there. But there's a lot of these technologies are helpful for real-world problems. But for me, what do all of these projects that seem different? First of all, what they all had in common is I myself never was in this field. I never knew anything about the Air Force operation or the public transportation or the fire department. I didn't even know their language, and they had to tell me exactly what they mean by their codes and but all of this I didn't know. This is what all these projects had in common, but they all have one way of solving them is the math does help you address all kinds of problems in not so different way. Once you understand it mathematically what they want to do, once you translate their language to your language, these solutions follow naturally. So that's another part of what I want to spread is if you learn the math of things, it's not really that hard to address all kinds of problems and to transfer your skills from one domain to the other. You do have to learn the vocabulary of the new domain that you're working with. The other thing is the project with the public transportation, the project with the on the bus project. And I always want to say this, for everybody to pay attention to what data they work with. So we actually did the model. We did a supply and demand model, and it based on based on social vulnerability of the population. Do they have enough bus stops, and is the route, and then based on when the ridership peaks, the bus riders. I mean, we did all the analysis. We did a model, say that takes input as the features of the population and the location and what type of time of the day, all kinds of input. And as I said, it's a function input output, and then the output was, say, the number of riders. I don't remember exactly. If I have to look at my notes. Anyway, so we did all of that. We came up with a model, and we were going to deploy it. Right? We were going to give it to the department and tell them, now you can assess supply demand this way, and now you can reroute this way at this time of the day, et cetera. It's a complicated thing, and it's actually very nice and stimulating. But here's what happened is one day before we were going to give them the models, I don't know what we noticed. Something was just not right. And then we looked more into the data, which was stupid for us, is we didn't do this before. And it was my fault because I was supervising my students, and I was I was trusting a bit more. I wasn't like paying attention 100% until the very last time, just because I wanted to double and triple check before we deploy. And then I told them to plot. I want them to see everything on ArcGIS, like just put everything you have there, and then the data they were working with, which was sent to us by the transportation department, we plotted like the route here. That was correct. The routes were correct that they gave us, and then supposedly each route had stops on it, and then we plot the route, and the stops, the way they were labeled, were like all over the city, not on the route. So seriously, our model. That could not be fixed from their side. So we were given the data that was fully scrambled, and that was on the database level, and it was horrible. And then we were going, and had we not double, triple checked, the transportation department was going to start making decisions based on a model that's trained on very, very bad data. So again, the quality of data and how much you have to be careful in checking it in all kinds of ways, make sure all ways you look at it before you start modeling and putting it in your Python, whatever. You have to make sure it's all consistent, and because there's a lot of responsibility that goes there. So that's another story I wanted to tell. How much time do I have? 7 minutes? Yeah, we started a bit late. OK, so if you could scroll down a little. A lot, actually. Scroll down. OK. So here, so usually what people get confused about, this is a slide on how to not get confused when you're in this field or when you're trying to learn a new model because you want to use it in your company, on your institution. So if you go down, so I kind of listed all the kinds of things you always want to be attentive to when you're working with a new model, or when you're trying to decide if you want to work with a new model, if you're trying to learn and enter into this field and do the theoretical and modeling part of it. So people, you always want to know, you always Are you training on real data or are you training on simulated data? You have more control over simulated data. You did it. You generated it. It's not like real with all its errors, etc. So you always want to like know exactly what you're working with, what would work for your benefits. In the modeling stage, you want to, are you using probabilistic models, deterministic models? So probabilistic models are the ones who hallucinate, right? Because your output is sampling from a probability distribution. Okay, so if you're sampling from probability distribution, you're going to randomly sometimes sample things that you don't want. Are you in the training phase of the model or in your predicting phase? Is your model already trained and you're just using it, or are using it and improving it? So you always want to know exactly where you're at, where do you stand. Is your model linear or non-linear? If you're working, say, with the transportation department or something, you're giving them some supply-demand models. What kind of models? Does your model capture reality with its simplicity? Is it simple enough that it's giving good results and that's enough, or does it need more complexity? So, and then if you're doing math, you have to always, a lot of these modeling need optimization steps. So if you're training them, you're minimizing the error between the model and the reality. You always want that to be small. If the moment you want to minimize things, you're optimizing in math. When you're optimizing in math, there's levels of how difficult it can be, right? So if you're dealing with a convex function, it has a minimum. So that's easy, right? So dealing with optimizing functions that are convex is easier than optimizing functions that are non-convex, but it doesn't mean that we don't have ways around things. So if you're like seeing from above like that, exactly where I'm at, what type of difficulty I have, then things kind of add up very easily, and then you can move from one field to the other, from one type of application to the other, because the underlying structure is not that difficult. You're asking yourself the right questions. So if you keep going down, scroll down, please. They're on their phones, like my students. So you scroll down a little. All right. So again, if you're talking probabilities, you're also in math. You're like the language that you use is always expectation. We always want to know what to expect, and the mathematical statements are always about expectation and variance. In math, you always want to control uncertainty. You don't like it to be unpredictable, right? So we always want to know exactly quantify how uncertain we are, and then usually mathematically that translates to statements on the variance of your the variable that you care for. So. You know what? I think that since the scrolling is not smooth, and I do have a lot to tell you, stories like that, how to make things not confused, etc. I do tell a lot of them in the book, but I can stop now and open it for questions because it's really not smooth. I mean, usually I go through way more faster, and but yeah, talk to me and I can show you more. There's a lot more here that's important. Yeah.
So yeah, we'll take a few questions, but a big round of applause for Hala and her speech. Thank you. Very good, very interesting. I took some photos. That's why I was on my phone. Anyone have any questions for Hala? Oh, Aaron, go ahead.
I know you don't have the time to properly answer this, but you did a lot of graphical stuff with the transportation and probably some other things as well. What are some techniques you use to take into account like the routing and stuff, like just high-level names of like how you did that?
What went into our project, the techniques? It was, first of all, the first step we had to do is collect the data, like the city population data. We had to get all of it, right, including like the demographics, the income, like all kinds of them, because they cared a lot about the social vulnerability and whether people who needed transportation the most had access or not. So that the first thing you in your mind, you're like, well, tell me what the population, where they're all located. And the next thing you want the stop data, like where are all your bus stops before routing, okay? I want to know exactly where a bus can stop. And then you can route later optimally, right? But and then after that, and then of course you have to define the variables that you think will be informative, right? This is all in the modeling stage. Like, tell me, as transportation department, what do you care for? And what usually, what are the variables you track, and whether these variables, you quantify them somehow? Do you measure them? Do you approximate them? Exactly what variables you care for? And of course, you can, after your analysis, you can come up with more variables for them, but you just want to know from a business perspective, what do they usually care for? What do they submit to the government to get funding? Because these are the ones you care for. So you kind of collect all of that. And then once you had all this data, then you just, then we tried to create a function, as I said, function where, say, the input are all of these variables, and the output is like, say, ridership at I don't know how they measured it at this time of the day. I'm making that up of my head now, out of memory. Anyway, so we did create functions and stuff. Now, as for routing and stuff, then you have to do you have to go on the operation research side of things, and I have a chapter on that on my book. Is like optimal routes between dots, but then you have some weights on each, right? You have the variables. So basically, there is a lot of operations research, routing problems in there, but that's only when you want to go to the routing side. If you're only assessing supply and demand, it was only putting the data, getting the data, organizing it, joining, blah blah, like the joins and then predicting. It was a simple, in my head, very simple machine learning model. Now the machine learning, now how you train that function takes input, output. Then you can try many models and see their performance, etc. This is why it's important to know that what each machine learning model exactly, what does it do and stuff, and then the limitations of that. So that's kind of, I don't know if I answered your question. Yeah, but this is kind of the kind of work that went into that project.
Good question, Aaron. Read the book. I'll take one more question. Go on.
And I was going to talk about reinforcement learning today. If my talk flowed smoothly, I was going to get to ChatGPT, like the attention mechanism, the reinforcement. The underlying math, as I said, is simple, but I could not do it. I could not scroll. Yeah.
Hello. Thanks for the wonderful presentation here. My question is, so you talked about the quantum and the basic math are very simple and you can apply to the problem. I like to understand how this basic model kind of fits on the quantum evaluation. Like when the quantum things come into picture, do you think the basic model, the linear, the probabilistic, deterministic model can actually adopt easily? Or what do you think will be enticing in that future?
What do I think in the future? Oh, wow. Okay, so I'm going to answer from a very limited perspective. I'm going to answer from the perspective of someone who did. I did my I did my thesis in material science, and and then trying to understand material, the behavior of materials, the properties of materials, for example, like conductivity and how much you can control them based on their structure and the way the atoms are arranged and the way like some external force or some external stimulator like changes the atoms and how they, and how the shape of the atoms and their orientation affect their properties. From the perspective of a person who did mathematical models of that kind of thing, it still fits because once you define you basically it really you start from what's the best way to what's the best math function, or it sometimes could be a math lattice, right? It's like where are you starting from in your math model, and then whether after you make the math happen, like I don't know, evolve a simulation, like you saw this di by dt, right? Like it's like a position evolving with time. After you've defined what your starting math is going to be, and you let it say evolve, and then see what that function is doing, and then you compare that with the experiment, or you use that to design an experiment, it still fits. In that sense, it fits. Does that make sense? It's like where you're starting from, your assumptions, mathematically, if your starting math is capturing reality, when you evolve it, it will also capture reality, and you can use that to design the experiment, or you can use the experiment to know where to start your math. It's like a feedback loop. So in that sense, it still fits. Actually, for me, the way I see it is the only way I can understand it. And once you start seeing things this way, it all adds up. I just posted on my LinkedIn an article that I read yesterday about topological quantum computing, and it's very interesting. And you can see over there like where the math is actually the starting point of the math. You can see it there, and then you can like, okay, this is like they're doing this. Eventually, you can see the math evolving into these topological structures, and the way they arrange themselves is helpful for quantum computing. So in that sense, I see it as the same.
Big round of applause for Hala again. Thank you.
Thank you. All right, I'll be around.
Couple things I learned today. I need to go back to school for math. She's wicked smart, and I need to read a book.
Yeah. By the way, this book, I just got it for me, for anyone. I have a problem in my shoulder, so I can't hold much weight. So I actually brought one book. So if anyone wants this book, I'll just like raise your hand. There you go.
There you go.